continue with tomorrow and next week. And of course, that just scratches the surface of what is really a very big subject. And as you know, probably, if you're taking engineering or physical science anyway, that they expect you to take the differential equations class, which at Boise State is Math 333. And they've usually tried to offer it out here in the fall, if there are enough people for it to make. So anyway, DE means differential equation. You can see that you don't want to write or even say words that are that long all the time. So it's any equation where at least one term includes a first and or a higher derivative of any higher order, so second order, third order, so on. And you classify the differential equation by whatever is the highest order derivative that appears someplace. So if it's second order, that means some term at least has a y double prime in it. If it's first order, then some term at least is y prime and nothing is higher order derivative. The focus in today and tomorrow's class and the applications next week are on first order differential equations, and there are a lot of important applications, some of which we'll see. The heart of the Math 333 course is solving second order differential equations where one term at least has a second derivative, because you get that if you do the electric circuit with an alternating current, a resistance, and an inductance, and a capacitance. And you also get second order if you're thinking of a spring and a mass and a shock absorber like on a car. And those have obvious connections to engineering and physics. So remember that an expression is anything you write in math. Terms are things that expressions that you hook together with plus signs and minus signs. And then factors are expressions you multiply or divide. So the terms then in a differential equation are separated with pluses or minuses. And first order means that there's a first derivative somewhere in some one of the terms. So the order is n, where n is the highest order derivative. I've said that already. So for a first order differential equation, thinking that the variable's x, just to be specific about something, the highest derivative is y prime, which you can also write as a differential quotient. Remember, we went through that when I was holding up the money. Same amount of gasoline, 2 10s or a 20, and so on. So with a first order, then, you can either think of your variable as y prime or as the differential quotient, and then this is actually a quotient, so you can separate it as a fraction. And this says that we can separate variables if we're talking about a first order differential equation. Now you cannot do that if it's higher order. You can write your y double prime with the symbols, the 2 up here and the 2 down there, but you can't treat that as a quotient. In other words, d second y and dx second are not separate. That's not a quotient of separate entities that would have an interpretation on their own, the way that dy has and dx has in the graph. Remember, dy is how far up to the tangent line from where you started out, and dx is how far over, left or right, you've gone. So if you look at something like problem 9 in the homework for tomorrow, if you're doing the written homework anyway, and similar things in the My Math Lab homework, problem 9 reads like this. If you have your book, you can look at it. And they tell you that x and y are positive. They have to tell you that so that you can split the square root of the product into the product of the square roots, which you need to be able to do. Remember that here, x and y could be both negative because the product would be positive, and this would make sense. But if that were so, these would not be real numbers. So that's in the conditions on the problem, and it actually has to be there to do what we're doing. Just a second here. Differential Equations book, and is a brief summary of the history of differential equations. You notice that the Bernoulli family, Euler and Leibniz, are the people who did the early work in differential equations, and all of them were differential quotient type people, so to speak, for writing their derivative. So it's not surprising that they, and I don't know exactly which of those people it is, coined the name differential equation, whereas actually they could just as well have been called derivative equations, because you have one when your unknown is the derivative, first or higher order. A differential equation is what has stuck. So I split up my square root of the product into the product of square roots. And then what I do is separate variables so that the x's and dx are all on one side, and the y's and dy's are on the other side. And it wouldn't matter whether you left the 2 on the left or put the 2 down here in the denominator. You could do that either way. So now I have separated the variables. So then the logic is that if the expressions are equal, you can put on an integral sign, and that results would be equal to within a constant. So you integrate this. Think of slapping an integration sign. So you add 1 and divide by the new exponent. You integrate this. You see, you can rewrite this way with x to the minus half, and then add 1 to that exponent and divide by the new exponent, and then put your constant. You could put the constant on either side, but the custom is put it on the right. And so then simplify your fractions. You get 4/3, and here you get a 2 and a constant. If you leave your answer like that, you have an equation that's defining a curve. A curve defined by an equation like this is what you call an integral curve, or another word for it is trajectory. A more modern term is trajectory, actually. And the idea is that you would get a trajectory for each choice possible of the constant. So you really have an infinite family of solutions. I'll show you some maple handouts in just a minute that'll explain this idea better than I can say it. But you don't know specifically what value to take here. So out of a family of curves that are shaped the same way, defined by this relationship where the different family members are determined by the different choices of constant, so there are infinitely many possibilities. Out of all of those, you would be able to identify a particular one if you have a point that the curve is supposed to pass through. In other words, if you have a value for y at a corresponding value for x, to have a point x comma y. And these families of curves are something that a system like Maple will draw, and as I say, I'll show you in just a minute. Notice that you could do a little algebra here. First of all, you could bring this term across to the left, and you could divide by 2 and say 2/3 y to the 3/2 minus square root x is another constant, which is half of the first constant. These constants are something that you never can evaluate as a particular number unless you know the coordinates of the point through which the curve passes. And so you can play fast and loose with constants in the way that I have here, because all you're saying is there's some constant to get if you know a point on the curve. And if you don't know a point on the curve, you can't get it. You just leave the symbol for it, which means then that there is an infinite family of curves of this shape where you go from curve to curve by choosing different values for the c. This is a standard game in differential equations, so if you can get that idea today, it'll help you not just in this class, but in a sense more importantly in the 333, where you spend the whole semester playing games of this sort. Okay, so I've said this. So then we have the concept of an initial value problem, and so that's I, V, T. So that's more than just a differential equation. You have a differential equation, and then you have values for the function y and all of the derivatives that would appear in the problem. And they're all given at the same value for x, that I'm calling x equal a. If you had your value for y at one place, x equal a, and a value, say, for y prime at another place, say b, which is different from a, you could have that kind of problem. And then instead of initial value problem, you call it a boundary value problem. In the 333 class, you do both problems of both kinds. That's getting a little deeper than this class gets, but there are initial value problems, there are boundary value problems. Both of them could involve the same differential equation, and which it is, initial value or boundary value, is whether you know values for y and y prime just at one point, same point, or at different points, which would then be your boundary. So definition then, y is a solution to an initial value problem when both things happen. Y will satisfy the differential equation, and also the solution you get, that I would be calling y, will meet whatever condition is given at some initial value point A. Doesn't have to be 0, might be. Often the initial value problem is related to values at 0 for y and y prime, but that's not required. It could be at 1 or something else, but its initial value, if you know y and y prime, thinking of a first order problem at the same point. And again, boundary value if it's different points. The reason I'm making such a fuss about this distinction is that from the point of view of the math department, the restrictions, if it's a boundary value problem, mean that you can get a differential equation and a function that'll make the left-hand side equal the right-hand side, but will not meet both the value at A and also the value at B, say, for y prime. So you can have boundary value problems that you really can't solve, whereas if it's an initial value problem, you generally would be able to solve it. So that the mathematical conditions are stricter if it's a boundary value problem. So look at something like problem 8. In this one, they're not expecting you to solve the differential equation straight up as I did with this. In this one, in 9, we have the differential equation and we separated variables and came up with a solution. In problem 7 and 8 in your book, they don't expect you to start with the differential equation and figure out that this is the solution. How you would do that with a problem like this is what we'll take up tomorrow, actually. But for today, they're giving you this, and they're giving you this as the possible solution, which it proves to be, and they're telling you that this solution is also supposed to give you the value E when X is E. See, Y of E would be E. So what they're asking you to do here is to take this and check, does X squared times the derivative of this, which would be your left-hand side, equal what you get if you put this there and multiply by X, and then put it there and square. And also you're to check that when X is E, the Y value is E. So we're trying to prove, like you prove a trig identity, that this works in the way that I described, and also that this gives you this value when X is this value. So the first few problems in the homework are check that it really is a solution without without the problem asking you to come up with this. You know, as I say, we'll see tomorrow how you would come up with it. So notice that there's the condition X is greater than 1, so you can do the log, and it would be positive. So you must do two things. You must show that your left-hand side, LHS, which you get if you differentiate and times it by X squared, is some expression which is also what your right-hand side gives. If you put this there times X and square this and add your fractions. And you also have to show that if you put E there and there, which would be Y of E, that this is what you get. You can see that it is because log of E is 1. So this does give you the correct initial value. Okay, so if you do Y prime, you have quotient rule. Denominator times the derivative of the numerator minus the numerator, derivative of the denominator, denominator square, right? Or if you prefer to be amused a little bit with a quotient rule, if you think of the numerator as high and the denominator as ho, which rhymes with low, then this recipe is ho-de high minus high-de ho over ho-ho. That's how you teach Math 160. Okay. So anyhow, you simplify this. Notice the x's cancel. And so there's your y prime. Now we're looking at the left-hand side. So x squared times that would be x squared times this, which I've put here. And then your left-hand side would be, if you go ahead with this, you have x squared log x over log square. And then you have minus x squared over log square. So getting a common denominator, you have the x squared log x minus x squared on top and log square. Meanwhile, if you look at your right-hand side, your xy, there's your x and then this is your y. So that gives you the x squared over log x. And if you want to rewrite that, you could multiply top and bottom by log x. So this first term in the right-hand side looks like this with this denominator. See, I want this denominator because that's the denominator of my left-hand side. So to see that they're identical, I want the same denominator. The other part of the right-hand side is y squared, which would be the x over log y quantity square, and that gets this common denominator for the two terms in the right-hand side. So your right-hand side, using this as the common denominator, is x squared log x minus x squared over log squared, and that's the same as the left-hand side. You can either factor the x squared out to see it's identical to this, or you could take this one and multiply the x squared through and make it like that. And as we already said, the y of e is going to be e over log e, which is e. So the given y of x satisfies the initial value problem because the solution does give the right initial value at the point where you're given your data, and your left-hand side does equal your right-hand side. So the first two or three homework problems are to do something like this. Suppose you look at 13, where you have dy dx is root y cosine square root y. So if you're separating variables again, multiply through by the dx and divide on the left by all the y's, and then for 1 over the cosine, you have secant. So you have secant square y, and then dy over square root y on the left, and you have dx on the right. So this is a, if you're going to do an integration to solve the differential equation, this is a u substitution problem. So if you let u be your square root y, remember that your derivative of the square root is 1 over twice the square root. So your du is dy over twice the square root. So what you have here then, dy over the square root is 2 du. So I can replace that with u and that with 2 du. And then put on my integration symbols. And I have secant square u and 2 du is the integral of dx, then plus constant. Okay, derivative of tangent is secant square. So you have 2 tangent here and x there. Then you can substitute to get back to y. Remember your u was the square root, so you have 2 tangent square root is x plus constant. And these are integral curves. The book has it this way where they move the x across, but this is just as good. Notice that with these, usually you don't try to solve for y as a function. You could divide by the 2 and then say root y is arctangent x plus a constant over 2, and then y would be the square of that. But usually you don't do that, and part of the reason for it is the way that a modern computer system handles these things. So maybe we should look at some maple here. Let's look at the maple, and we'll get back to the integral curves like I was talking about here after we turn a page or so with this. Maple has the command dsolve, and so you type dsolve, and then any maple command, after you get done typing the letters, you have to put in a parenthesis. And then you have to write your differential equation, and if you are doing an initial value problem, you have really a system of equations, because the differential equation is one equation, and then the initial value, y of 0 equals. Well, for example, with this. This is a system, really, of equations. There is the differential equation, that's one, and then the initial value is an equation, y of e equals e. So you notice that the one that I have here, then I have, I'm using the capital letter D as the derivative. You can do your derivatives in maple with capital letter D, parentheses, whatever is the function. So D applied at y applied at x is dy dx. Plus y. Again, you don't just write y, you write y of x, because it's a function of x. So you have to get that right or it won't work. And then what's on the right-hand side? I think this is problem 5 in 7.2. It's one of those where they give you the solution and want you to prove that it does work the way that I did with problem 8 and does meet the initial value. What I'm doing with maple is writing the differential equation, and the initial value is a system, and getting maple to solve it, which of course it will do. So I have my derivative plus y is 2 over 1 plus 4 e to the 2x. And then my initial value, y at minus log 2, is pi over 2. So the place where you have this initial value is not 0, it's minus log 2. And then you notice you're solving a set of two equations, the differential equation and the initial value. So that is in the set braces. See, there's D-solve, and then there's the parenthesis, and then there are the set braces. That's because you're solving the system. Finally, you have to say what you're solving for. You're solving for y of x. And then after the y of x, you have the parenthesis that matches the one that came after the e in the D-solve. Whenever you're using parentheses or braces or brackets, they have to pair up. And you'll get a nasty note back in red ink if they don't, at least if you have a color printer. So finally, you see the solution, e to the minus x arctangent 2e to the x. And as I commented, we solved a system, the dE equals, and then the y at minus log 2 equals. So I've done some of the other problems with D-solve. You see 11 was not an initial value, it was just solve the differential equation. And then 13, which we just did here, I did the D-solve, and you notice that the answer is a horrible looking mess, and you can tell it to simplify, but it's still the same mess. So sometimes you can actually do something better yourself by hand than what something like Maple will do with it. Notice that the way Maple writes its constant is with the underscore and the big letter C, and then the I there. I don't know exactly why Maple wants to write its constants that way instead of just simply the letter C, but that's what it does. So to try and get at the idea of integral curves or trajectories.
I'm sorry, I think that's a 1, isn't it? Like the number 1?
Okay, C1 then.
I think so.
Okay, well, whatever it is, I don't know particularly why the underscore. That's what I was trying to get at, to the left of the C, but it does that. Okay, so look at where it says section 9.1, number 1, with DE tools. The second here. If you're looking at the bottom of the first page there with the Maple, if you bring up the package DE tools, then what I'm calling DE1, I'm defining it, you see, so that this differential equation has the name DE1. So DE1 colon equal the derivative equals x plus y of x. Okay, so it's y prime equals x plus y is what it would be if you're saying it in simple words. And then if you say DE plot, which is one of the tools in this package, instead of retyping the differential equation, since you've given it the name DE1, you can say DE plot, DE1, and then comma, y of x. So that's telling Maple that you're thinking of x as the independent variable and y as the dependent. And then you have to give Maple some sort of region in which to do this plot, some sort of window. So it can be whatever you like. I did x is -4 to 4, and y is -4 to 4. So you see this rectangle that is on the first page there. And those little arrows are what we call isoclines, a word which I should write down. So the word origin is Greek words. Iso in Greek is the same or like. We have lots of different uses of iso in English. Isosceles triangles are two sides that are the same length, and we have isotopes in regular inorganic chemistry, where you have the same chemical properties and different atomic weights. You can turn your head around and look at the periodic table. And you have isomers in organic chemistry, where it's the same count of hydrogen and carbon, but different structures, so they do very different things, and on and on and on. So iso means like. So isoclines then have like slope. And you see your first derivative, which we're talking about, first order differential equations, your first derivative gives you the slope. That's what it is, isn't it? So you can look at it that the different values for x and y that you get from the original differential equation, that those are producing this field, as it's called in red here, of little slope lines or curves, which are the slopes at each point. So we can enter initial values if we want to, and that's what's going to tell us what we mean by getting on a trajectory and following it with our choice of the constant in our solution, trajectory or integral curve. So DE plot, the differential equation, and again, by writing the y of x, you're saying that the slope would be dy dx. If you said x of y, you see, then you'd be saying your slope is dx dy. And the window. And now you see I've put in 4 different choices for an initial point. And so I'm going to get 4 different trajectories in the picture when I turn the page. So if you turn the page, you notice also I have it on a bigger scale than the first picture. You see the isocline field, as it's called, and then you see these various trajectories, how the yellow curve follows the path of the particular set of isoclines. And if you look carefully, you can see, for instance, where 0 minus 1 or 0, 1, you can identify those points and see that they're on the one or the other of those yellow curves. Then for my second different example, DE2, example, as I was saying, DE2, it's dy dx equals y plus 1, or y prime equals y plus 1. But when you're doing the work with Maple, you don't write it with the differential quotient. It's not set up to do it that way. You write it with capital letter D for the derivative, parentheses y. So it's like y prime, but this is how you write it. And then I have the DE plot with some selection of initial points. And again, if you look at the yellow curves, you can, and then look at coordinates of different points, you can see how they're on one curve or another. Then with my DE3, where I have the x over y of x, this upset Maple because you had the y and I had the y in the denominator. And if you tune all that out by turning the page, sometimes the way to live with a computer is just to tune the thing out and go on. Turn it off and turn it back on or something, let it reboot. But anyway, after all this protest, you see, it finally does the picture. So what the integral curves are doing with that one is going around in a circle. And then DE4, you know, this is y square minus x square, and you can see that the integral curves are hyperbolas. If you look at the yellow curves, notice that I have something here where I have the y square minus x square curves. So the DE4 is related to what I have here that we'll do by hand. So the point is that with a modern computer algebra system, you have these integral curves or trajectories, and there really are infinitely many, and which one you're on is defined by what your choice is for your initial value. Okay, so back to doing things more by hand. If you look at 18, you notice that this is very nonlinear because the y, when you go through this, it appears as the argument of another function. First of all, what you do, as you know, when you multiply powers, you add or subtract exponents. So this is a product, e to the 2x, e to the minus y, and so is this. And then when you have the same base and the same letter in your exponent, if you have a quotient, you subtract exponents. So this e over this one, you can write this way, and this one over that one, you could write by subtracting exponents, and then with the negative exponent, you can put it in the denominator, and 2x minus x gives you x. So finally, you have e to the 2y. You separate variables, dy equals e to the x dx. as I'm saying, this is not a linear differential equation because your y appears as the argument of another function. I have linear defined over here, so I guess I was using a term we hadn't come to, but when we get over there and talk about linear and not, keep this in mind as a good example of not linear. This one also. So anyway, continuing with 18, we've separated the variables so we can integrate on both sides. And so this is really U substitution on this one. And then if you want to, you could multiply through by the 2, and this constant times 2 would just be another constant. So you could write your trajectory or integral curve like this. 20 is a factor by grouping problem. You're given this. You notice this one is linear because the y is first power where it appears. And also notice that x is a common factor in those two terms, and that minus 2 is a common factor in those two. And then when you do that, you have the common factor y plus 3, so you can factor that on the right, and finally write your derivative or differential quotient as a product like that. You should remember doing stuff like this in algebra. That's one of the things they like, isn't it? Is the factor by grouping sort of thing. Well, anyway, you can separate once you get it written as product of factors, because you have only x in this factor and only y in that factor. So you can separate like this and integrate, and then write your integral curves. Say, bring these across, something like that. And I would not try to solve for y here. It's possible, but it's not really worth anything, because the way that you would study what's going on is with DE tools or its equivalent in Mathematica or MATLAB, and so you'll get these isopline fields. Then you can get the computer to draw the integral curve corresponding to any particular initial value you want. Look at 22, which starts out like this. And this also is a factoring game. So here you can write the product of factors. And so you see an e to the x here and one there. And then you have the e to the minus y plus 1. So if you factor the e to the x in those two terms, you have then on the right e to the y plus 1 here, and you can think of this as 1 times e to the minus y plus 1. Okay, so then that's your right-hand factor, the same way that y plus 3 was here. And you have the blue for your left-hand factor. So now you can separate, because you can take this under the dy and take the dx times this one. And then you can notice there's another trick here. This is more like the first part of chapter 8, which we were doing about 3 weeks ago, where you're doing integration with tricks. if you multiply and divide this fraction by e to the y, which is legal, and multiply the e to the y through down here, you get 1 plus e to the y on the bottom, and this e to the y dy on top. So if you call that u, this is du. So that's pretty tricky, but it works. It's pretty slick, actually. Because you look at this, how do you integrate something like that? But you do this sort of thing. Now you say u is 1 plus e to the y. This is the du, so your integral is log. And over here, term by term, e to the x takes you to e to the x, 1 takes you to x, plus constant. So then your integral curve, if you want to, you can take these to the left and write it like that. Well, I've dropped the name linear, so the definition is that the differential equation is linear when no term contains the letter y, including y prime, y double prime, etc., more than once. This is per term, and also they appear only to the first power in any term where you have them. So this first part means that it's no longer linear if you have a term that looks like y times y prime, which you could have. And the second part means that something like this is not linear, where the y appears in the exponent position. Something like this is not linear because the y appears in an exponent position. Something like this is not linear because the y is not first power, and also it appears in the argument of another function. So there's 2 strikes against this one being linear. This one is not linear because the y is squared. See, it doesn't appear to the first power anytime you see it. It's linear in this term. It doesn't hurt that it's multiplied by x squared because that's a different letter. It's linear here. It doesn't hurt that it's multiplied by x. Linear doesn't mean that it has to be constant coefficients. But it does mean that in any term where you see y, it has to be first power, or y prime has to be first power. And it only appears once in a term where you do see the y letter complete, including y prime or y double prime. Let's see. Here it's not linear because the y is under a square root sign. It still is, even if you break that up. So these problems are mostly not linear, but nevertheless, it turns out that linear first and second order differential equations have many important applications. The electric circuit and the mechanical circuit differential equations are second order, but they're linear. And we'll talk about how you solve the first order linear equation in the general situation tomorrow, and we'll talk about applications of first order linear equations. So meanwhile, look at something like this, for which I have another handout. Application that we could finish with today is orthogonal trajectories, as they're called. Orthogonal means the tangents meet at right angles. It's a big word for perpendicular, although perpendicular is about as big a word, I guess. So I have the red curves, and a typical point, the tangent would be T1, and the blue curves at right angles, tangent T2. So the T1 and T2 are perpendicular, and as you know, for perpendicular lines, if they're not vertical or horizontal, you can get slopes, say M1 for the red and M2 for the blue, and the product of the slopes is -1. That statement breaks down if you have a vertical line where your slope's not defined, or a horizontal line where the slope is 0. But other than that, something like my picture, the product is -1, or as they say it, the slopes are negative reciprocals, right, in geometry. So your blue curves are typically hyperbolas that use the axes as their asymptotes. So xy equals a constant. And so then what we're after is to see that the conjugate family, which would be hyperbolas that meet at right angles, in the sense of my picture, will have an equation like that. So what you could begin either way, but say you begin with the blue ones, xy equals a, where a is a constant. And different choices of a are how you get from one trajectory to another, you see. So differentiate both sides with x. You're thinking y is a function of x. So product rule. So the left times the derivative of the right plus the right times the derivative of the left, which is 1, and the derivative of the constant is 0. Okay? So that means you could solve for y prime, or dy dx, as minus y over x. And write your differential equation with the differential quotient so you can separate variables. Okay, so this is the slope that I've been calling M2. And the slopes M1, M2 are -1 because they are at right angles. And so that says that M1, which is dy dx for the second family, the family for which I'm trying to prove this is its equation, would be -1 over M2 for the first family. So -1 over the slope here for the first family, the blue ones, minus y over x. So the minuses cancel, and you get, for the red family, dy dx is x over y. You can separate the variables there and get your conjugate family. So you might think, well, what does this mean? Well, here it is in the real world. Okay, what's this? Ring and pinion, right? It's actually out, I have a 1968 Skylark Buick. It's actually the original out of the rear end of the Buick. Okay, so you get them in the right place here, and these curves fit together, you see, which makes the rear wheels turn and makes the car go, provided the engine will run. And like all Buicks, it'll run fine as long as you don't try to go past a gas station. You can pass everything but the gas station. So anyway, these are conjugate hyperbolas. This type of rear axle was developed in the early 1930s by the Packard Motor Car Company, and having it this way allowed you to make the car a good deal lower to the ground. The cars before that time had this up, and this part would be underneath it, what they called spiral bevel. So the cars, compared with the 1920s, became much lower to the ground, and being able to position it like this is partly why. So you think that all this math is really just a game, but actually people really have used some things that you have developed with math in the world. So here's a good example. So I'll leave this if anybody wants to study car mechanics in the class. We'll see how they are made. So what we'll do tomorrow then is we'll talk about the how you solve the general first order linear differential equation, and we'll do some more applications, and then some more applications next week. So see you tomorrow.